Yeah, you can just make it up when you come back, either, or you can take it before. Either way, it doesn't matter. Yeah. All right. So this problem says when water freezes, its volume increases by 9%. Okay, that's quite a bit. That's one of the reasons why ice floats. Okay, so its density gets less than water. What forces per unit area is water capable of exerting on a container when it freezes? Okay, so the way we'll do this is, let's say here's a volume of water, and then you decrease the temperature and it freezes, and when it freezes, its volume increases. Okay, so if you want the container to keep that water within the container, it has to apply a force, and the force per unit area is what we want to calculate. Okay. Force per unit area is what we want to calculate. That is the force that the water is exerting, and so if you want to keep the water in, that's the force the container must exert. And most containers can't do that. You can take any man-made material, put water in it, and completely fill it with water and freeze that water, and it'll burst. That's my guess. Okay. So let's find. What is the bulk modulus of ice? Okay, so the bulk modulus of ice is 9 gigapascals. Okay, so what this means is bulk modulus is force per unit area. Okay, so as the water, as water freezes, it's expanding, so it's exerting a force on this container, and the container is having to exert that equal and opposite force to keep it in the container. Okay. So what is the force per unit area that you have to exert to keep it in the container? Okay. So the bulk modulus of ice is that. You want to decrease its volume. By how much do you want to decrease its volume? 9% to keep it in that original volume. Okay. So the force per unit area that you have to exert is equal to B times and the bulk modulus is 9 into 10 to the 9 pascals, and this is 9%. The change in volume divided by the original volume is 9%, which is negative 0.09. We'll just say 9%. You have to reduce the volume by that. Okay, so this is 81 times 10 to the 7 pascals. So the force you have to exert is that, and let me put that in perspective. You guys remember 1 atmosphere is roughly 10 to the 5 pascals, and that's equal to about 15 psi. What does psi mean?
Pounds
pounds per square inch, okay? So the atmosphere is exerting every square inch, it's exerting a force of 15 pounds, okay? Uh, Now, that number might seem small, but here's a sheet of paper that's 10 inches by 10 inches. That's 100 square inch. 15 times 100 square inch is 1,500 pounds. So the atmosphere is exerting a force of 1,500 pounds on the sheet. 1,500 pounds, that's the weight of 10 people. Why isn't this flying away? There's an equal and opposite force, okay? So 15 pounds per square inch is quite a bit of force, okay? So that's one atmosphere. So the force per unit area that the water exerts as it expands, as it would expand, is this much. Okay, so let's write this. 80, I'm going to write this as 8,100 times 10 to the 5 pascals. So 8,100 atmospheres. That's enormous. Okay. So this is, so let's say this is 10,000 times 15, 150,000 pounds per square inch. That's the kind of force that ice would exert as it expands. Okay? And that's why you put a bottle of water completely full in the freezer, and that bottle will burst easily. Okay? And like I mentioned before, in countries in climates where water would freeze overnight if it got cold overnight, and in the old days, if you wanted to quarry marble, for instance, in Italy, what they would do is, so here's a mountain, you would make a groove in this rock, pour water in it, and then at night when the water freezes, it pushes this slab off. Okay. That force will crack that slab. And yep. All right. So a disc between vertebrae in the spine is subjected to a shearing force of 600 newtons. 600 newtons is roughly your weight. Find its shear deformation using the shear modulus of 1 gigapascal. The disc is equivalent to a solid cylinder, 0.7 centimeters high and 4 centimeters in diameter. Okay, so what they're asking you is the following. So this is 0.7 centimeters and the radius is 4 centimeters. So the disc diameter is 4 centimeters. Okay, so the disc is about that big, okay, and this thick. And what you're doing is you're applying a force of 600 newtons. And what they want you to find is the shear deformation. So the shearing stress, the shear modulus is again stress over strain. Strain this is delta x. That's the displacement of the top surface relative to the bottom surface. And this is h. So delta x over h. Okay. What they're asking you to find is find the shear deformation. This is what they're asking you to find. Okay. So delta x by h is f over a divided by s. Okay. And the area is the area of the the disc is circular from the top view, that's how it would look. I guess it's cylindrical. So the area is force over 4 pi r. It's pi r squared. Okay. So force is 600 newtons. Pi radius is 2 centimeters square, and the shear modulus is 10 to the power 9 Newton per meter square. Okay. So the units would be, this cancels with that, and meter square cancels with that. So this is a dimensionless number. That's this shear deformation divided by the distance. Okay. So this works out to, so let's take our powers of 10. This is 10 to the minus 2 times, that becomes 10 to the minus 4. That gives 10 to the 5, and 2 cancels, so 10 minus 3. So this is 10 minus 3, 6 divided by pi times 4, 4 pi. Okay, so delta x by so 6 divided by 4 pi is 0.48. Okay, so if you multiply this by 100, you get percentage. So 0.048%. Okay, so that's how much the disk deforms. Okay, so what this means again, so it deforms ever so slightly. Okay, so this is delta x, and this is h. Okay. So it turns out that if you bend over to lift a box like that, that's the kind of shearing forces your back will bear. Okay. And even though the shear deformation is small, you can cause damage. So that's not how you lift objects. You guys might have heard you lift objects like this with a straight back. Right. Calculate the force a piano tuner applies to stretch a steel piano wire by 8 millimeters if the wire is originally 1.35 meters long and its diameter is 0.85 millimeters. Okay, so we'll draw it like this. And you want to stretch the piano wire. Okay. What you learn in the little later, the speed of the wave on a piano is the tension divided by mu, the weight per unit length, which is the frequency times length. So when you're applying a tension and stretching, increasing the tension, the wavelength that it plays just depends on the length, so you're not changing the length much. So by increasing the tension, you're making the piano string play a higher pitch. The frequency is increasing, so that's what you're doing. Okay. So if the tension in a piano wire decreases, it plays a lower pitch. So to tune it back, you have to increase the tension to bring it back to its original frequency. All right. Now we're looking at from a different perspective here. So you're applying a force and you're stretching it by 8 millimeters. 8 millimeters is less than a centimeter, so 0.8 centimeters. It's about that long. Yeah. And it's 1.35 meters, I guess, so almost from the ground to your shoulders. Okay. And the diameter is 0.85 millimeter. All right. It's a steel piano. Okay. So the Young's modulus is given by force divided by area times the change in length divided by the original length. This is stress over strain. Okay, so what we're calculating is the force. So the force is this A comes to the bottom, so it's Y times A times delta L by L. Young's modulus, and A is the area of cross section, okay, which is a circular cross section, pi r square, delta L by L. All right, so let's look up Young's modulus for steel. The Young's modulus for steel. So Young's modulus for steel is 200 gigapascals. So the force you're applying is Young's modulus times pi r square times delta L by L, 200 into 10 to the 9 Newton meter square. Pi, the radius is so half of that, so 0.425 millimeters, which is that many meters squared. Delta L is change in length is 8 millimeters. Increase in length is 8 millimeters, 10 to the minus 3 meters, and the length is 1.35 meters. Okay, so that is the force you would have to apply to stretch that wire. So the wire is 1.35 meters, and you're stretching the steel wire by that much. Less than 1%. You're stretching it by less than 1%. Okay, so this is 10 to the 11. That's 10 to the minus 6 and 10 to the minus 3. So 10 to the minus 11, minus 9 will kill that. So that would be 200 times pi times 0.425 squared plus 8 times 8 divided by 1.35, and newtons is, okay, the meter square will cancel, meter cancels, and you're left with newtons. So this works out to 670 newtons, your body weight. Okay, so that piano tuner is applying a force of 600 and your body weight worth of force to stretch that piano string when he or she's tuning. Okay. All right, so a suspender rod of a suspension bridge is 25 meters long. So if you guys have been on any of those bridges, um, where there's a nice suspension bridge in Jacksonville on 9A, if you've been on that. So this is the rod we're talking about. Okay. And it says it's 25 meters long. 25 meters long is roughly the width of this room. So that's how long that cable is. Yeah. It's made of steel. What must its diameter be so it does not stretch? So they want you to find how thick must it be so it does not stretch more than 1 centimeter. So you want this cable to stretch 1 centimeter. Okay. When a truck passes by it, so a truck is passing by, and we'll say all of the weight of the truck is being supported by that cable, and that's roughly true. Yeah. All right, so here's the cable, and you want to stretch it by 1 centimeter. Yeah. And what you're doing is finding the radius of this guy. Okay. So Y is, again, force. Again, this is made of steel, and there's the Young's modulus for steel. Yeah. So what is it that we're trying to find? Delta L. So delta L over L equal to F over we're trying to find the radius, so we're trying to find A. Yeah. All right, so A is pi r square. So that's the radius of that cable. Okay. And you guys understand, the thicker the cable, so smaller the stretch, thicker will be the cable. Okay. And this is a well-known thing. You guys have bought rope and stuff like that. What do they do with rope? They take thin fibers and twist it and then make braids out of it. So it's stronger that way. They do the same thing with steel cables as well. Okay. And you might even see that with new Apple cords. In the old days, all those plastic ones would always break, and now the cables are wrapped around corded cloth and stuff like that. All right, so let's find that. Okay, so force is mg. Okay, so the mass of the truck is, so here's the truck passing by, is 2.5 times 10 to the power 4 kgs times g is 9.8 meters per second square. Pi, y is 200 times 10 to the 9 pascals, Newton meter square. The length was, you wanted it to stretch by 1 centimeters. 1 centimeter is 10 to the minus 2 meters, and the length of the cable is 25 meters. And this whole thing to the power half. All right, let's take care of powers of 10. This is we'll kill this 2 zeros with these things. That's 10 to the 9. There's 10 to the 4, so that comes up, becomes 10 to the minus 5. And we'll make this 25, and that'll make 10 to the minus 6. And then to the power half is 10 to the minus 3. So R is 10 to the minus 3. That became 25 times 9.8 pi 2, and then this was 1 over 25. Okay, so that 25 comes to the top, and this was all to the power 1/2. So that'll come out. So it's R is 25, 9.8. Okay, so roughly 3 inches. That's how thick that cable is. Each of these cables. Well, 3 inches is. Okay, so a cable that thick stretches 1 centimeter every time a truck passes by. All right.